The James Webb Space Telescope is about to revolutionize humanity's comprehension of the cosmos. On its 5-year mission, it'll gather heretofore unimagined insights into the birth of galaxies and offer a realistic shot at finding life on other planets. Or some worry it'll simply fall apart during its insanely complicated deployment. Are our collective minds ready to be blown? Let's hope so. Join us today as we look into the James Webb Space Telescope. Theoretically posited as a successor to the famous Hubble telescope back in 1989, what eventually became known as the James Webb Space Telescope, or Webb after science-mad NASA Administrator James E. Webb, has 4 broad mission goals: to peer across the gulf of space, and therefore back in time, to examine the formation of the very first galaxies, to investigate the birth of stars and planetary systems, to compare early galaxies with their more recent relatives to test theories about their evolution, distribution, and the role of dark matter. And finally, most excitingly, to assess the chemical makeup of distant planets, including our own solar neighbors, to accurately discern their potential to harbor life. So how is Webb different to Hubble? Hubble had a 7-foot 10-inch mirror. Webb has a 21-foot mirror. Size matters when you're capturing light from distant worlds, just as a bigger bucket will capture more rainwater than a smaller bucket. More important than Webb's size is its operational wavelength. Hubble was designed to capture light in and around the visible spectrum. That helped it generate ravishing images like these, which delighted and inspired a generation of stargazers. But visible light has several limitations. Webb sees in infrared, and as such, it's technically more akin to the lesser-known Spitzer Space Telescope, only 60 times larger. Why infrared? For one, it enables scientists to peer further away and further back in time. The first galaxies formed some 13 billion years ago, and owing to the constant expansion of the universe, the wavelength of the light they produced has been progressively stretched from its original blue and white wavelength into the red spectrum. So if you're not looking in the infrared, you won't be able to see them. More excitingly, red light's long wavelength means it can pass through irritating obstacles like dust. That means Webb will, in effect, see right through these gorgeous but maddeningly opaque dust clouds that baffled Hubble. That alone opens up great unfathomable expanses of sky for astronomers to pore over, again, for the first time ever. So what actually needs to happen on the Webb mission before we get to ogle those pesky hiding galaxies? All being well, in late December, Webb will blast off from the European Space Agency, the ESA's, spaceport in Kourou, French Guiana, on an Ariane 5 rocket. Webb is an international collaboration, by the way, between project leaders NASA, the ESA, and the Canadian Space Agency. Its ultimate destination is the appropriately Gallic-sounding L2 Lagrange point. This interplanetary sweet spot is one of only 5 locations in space where the gravitational pull of our Sun and that of Earth balance the centripetal force spacecraft need to move alongside them. What? Put simply, conditions at the L2 Lagrange point help Webb use gravity to save fuel. But this location is also useful for other reasons. As it moves through space, essentially parallel with the night side of Earth, Webb will always be in range of NASA's Deep Space Communications Array. It'll always have sunlight to power its solar cells, and because it's always moving, over the course of a year, it'll eventually have a clear view of the entire sky. Webb has a packed itinerary on its million-mile voyage out to the Lagrange point, unfurling its delicate machinery from Ariane's compact fairing like a high-tech butterfly emerging from a chrysalis. In total, some 178 release mechanisms all need to work perfectly. No wonder there's thousands of anxious space nerds nervously awaiting this particular launch. Anyway, half an hour after blastoff, the first solar panels will deploy. After 2 hours, the communications antennae will unfurl. 10 hours after that, the first of 3 course correction maneuvers will occur. Remember, everything has to work just so. Within a day and a half, Webb will have soared past the moon's orbit. A day after that, the sun shield will commence its steady, painstaking deployment. Less eye-catching, maybe, than those giant gold mirrors up top, Webb's sun shield is nevertheless a critical piece of kit. About the size of a tennis court, the 5-layer shield is designed to keep the actual telescope as cold and dark as can be. This is essential when you're working in infrared, as any interference would be catastrophic for the mission. The sun shield's kite-shaped structure comprises 5 shiny gossamer-thin layers. The 0.05mm thick outer layer is expected to absorb temperatures of around 260 degrees Fahrenheit, while the 4 other layers, each around half that thickness, progressively reduce heat transfer to the point the telescope gear itself maintains working temperatures as low as minus 447 degrees Fahrenheit. The membranes themselves are made from heat-resistant Kapton and coated with a 100 nanometer film of aluminium aluminium and a 50-nanometer film of silicon, doped in order to be electrically conductive. Just unfolding and tensioning this heat shield, which occupies much of Webb's first week on the road, involves 70 hinge assemblies, 400 pulleys, 1,312 feet of cable, and 8 deployment motors. And if any of that fails, the $10 billion mission may as well abort straight away. No pressure. Week 2 of Webb's galactic odyssey focuses on the telescope itself. Around day 10, a 25-foot tripod will extend, incorporating Webb's secondary mirror, which captures light from the primary mirror and directs it to the tertiary mirror, and thence to its scientific instruments. An additional radiator will also emerge for that all-important heat reduction. Over the following days, all 18 hexagonal primary mirror segments will slowly unfurl, with their finely calibrated hinge mechanisms and 132 actuators designed to help the mirror attain its perfect final form. The mirrors are made from beryllium, chosen because beryllium is light, strong, and robust at holding its shape across a vast range of temperatures. Each hexagon is coated with a layer of gold just 700 atoms thick. Why gold? It's the optimal material for infrared astronomy, apparently, and a smart flex on behalf of humanity if we bump into any especially bougie aliens. A month after its launch, Webb's final course correction will put it into a halo orbit around the Lagrange point. This is when the cooling begins in earnest. Project leaders reckon a week will be needed before the NIRCam, or near-infrared camera, which calibrates and irons out any imperfections in the mirror alignment, is cool enough to function properly. 3 weeks after that, the shady portion behind Webb's sun shield will cool down to the necessary minus 380 degrees Fahrenheit, or 40 Kelvin, for work to begin. One of several design innovations Webb employs to lower its temperature is its distinctive open structure, as opposed to the familiar self-contained tubular format of Hubble and the telescope in your attic. Still, even that isn't cold enough for the MIRI, or mid-infrared instrument. It needs a dedicated cryocooler to chill it still further, down to a refreshing minus 447 degrees Fahrenheit, or just 7 Kelvin. That takes 100 days, by the way, around the same time needed to perfectly align those gold mirrors. After a few more days calibrating its onboard instruments, Webb will be good to go. What will the instruments be doing? 2 things broadly: taking photos and capturing spectra. What are spectra? Spectra is the plural of spectrum. Webb is equipped with 11 distinct modes of spectrograph. These employ a mixture of clever filters, smart detectors, and fine microshutter arrays to break down light from distant objects into their component colors. Why? To enable scientists, for the first time, to directly observe the chemical makeup of countless distant worlds. That's a huge deal, because the presence of certain elements, say methane, might indicate the presence of alien life. All being well, Webb will be relaying images back to our spellbound species by summer 2022. We'll get to see further away and further back in time than humans have ever managed before, and that in itself should lead to some striking discoveries. Everything hinges on that delicately choreographed launch and deployment sequence, though. Some mind-bending engineering has gone into its planning. For instance, we all know most materials shrink at ultra-cold temperatures, so Webb's designers have built many of its components precisely wrong, so they shrink to the perfect size and dimensions in situ. Why is that so nerve-wracking? As NASA mission systems engineer Mike Menzel puts it, when you're a million miles away from Earth, you can't send someone to fix it. What do you think? Are we on the cusp of a new era of discovery? Let us know in the comments, and don't forget to subscribe for more web-slinging tech content.